Thank you for dropping by our poster about observation-constrained multi-cycle dynamic models of the southern San Andreas and the San Jacinto faults. Multi-cycle dynamic models and physics-based numerical models in general have the potential to link observations from different fields, and it will help to address uncertainties in the earthquake phenomena and lead to a multidisciplinary understanding of earthquake dynamics and eventually better forecasting. There are several keys in multi-cycle dynamic models: realistic fault geometry, earthquake cycles, and dynamic ruptures. The diagram here shows dynamic ruptures and the interseismic deformation on realistic fault geometry will lead to heterogeneous stress. And this heterogeneity will contribute to the complex earthquake rupture dynamics observed in nature. For this study, the fault geometry is from Community Fault Model 5.2, and we get the fault geometry at 3 kilometer depths in our model. The method includes EQDyna 2D, a finite element software for seismic dynamic ruptures, and an analytical solution, viscoelastic solution for interseismic stress evolution and as a proxy for our fault damage. And we use slip and rate weakening law to take account of rate dependency during dynamic ruptures. The maximum shear straining rates and the directions are input in our model, and they come from geodetic data sets. After the simulation, we compare our results to long-term slip rates and the slip per earthquake estimation. These results shows the slip distributions of the earthquake sequence over 4,000 years in Model A. So the loading conditions are shown here. It is parallel to the fault segments north of the Big Bend and shows slightly compressional environment south of the Big Bend. There are 3 types of ruptures in the system. Type A ruptures, it breaks the whole fault system, and type B ruptures is impeded by the Big Bend, and we have type C ruptures. It breaks parts of the San Andreas faults or individual segments of San Jacinto faults. Important information from the model is the possible epicenters, and it is important for ground shaking evaluation. For example, these two type A ruptures could either nucleate near Cajon Pass or north of the Big Bend. The long-term slip rate from several models are presented here. They generally show the decreasing trend from north of the Big Bend to the San Bernardino segments. And the details of the value depends on the static friction level of the fault system and also the viscosities in the model. We care about whether we can reproduce past ruptures from paleoseismicity. The figure here from SCEC and Yule 2020 is the most updated knowledge of past ruptures from paleoseismicity. And in our model, we can reproduce ruptures like this one that stops somewhere past the Big Bend. And also we can reproduce ruptures that break individual segments of San Jacinto fault, like the Claremont and the Clark segments. And in some scenarios, we have ruptures that break individual San Bernardino segments. And an interesting scenario is this one. It breaks the whole fault, San Andreas fault in our model. And also there is a potential that San Andreas fault and San Jacinto fault that break at the same time. And our model shows it is potential. So thank you for your attention. We can discuss more at the poster. Thank you.